Okay, so now we're doing covalent compounds, which means either metalloids and nonmetals or just nonmetals. The difference with a covalent compound is there is a discrete unit. There are some compounds, like this is an actual compound, nitrogen dioxide. This is also an actual compound, dinitrogen tetroxide. But if we do an empirical formula problem and we end up with moles of oxygen over moles of nitrogen, for both of these, it's going to be this answer. For both of these, there's twice as much oxygen as nitrogen. Twice as much oxygen as nitrogen. So for things that are molecular, when you do an empirical formula, you're coming up with the lowest whole number ratio, but it may not be the actual molecule that exists. If this was the molecule I was shooting for, I would come up with an empirical formula that looks like this. But I know that the molecular formula is really double that. So just understand that with things that are ionic, once you've come up with the formula, it's the formula. But for things that are molecular, there could be an extra step. Okay, so here we have phosphorus and oxygen. A 2.5 gram sample of the compound means phosphorus and oxygen. And then 14.1 grams of oxygen, we can subtract those to see how many grams are phosphorus. Even though phosphorus is one of the polyatomic elements that we know, for an empirical formula, we're just going to use phosphorus atom by atom, understanding that it's becoming stable by sharing. Not necessarily sharing with other phosphoruses. In this case, it's going to be sharing with oxygens. So even though here oxygen means O2, for the empirical formula, we're just going to write O and understand that it's becoming stable by sharing with phosphorus. So the way to get these to whole numbers, the way to make 2.5 into a whole number is to multiply by 2. But if I multiply the oxygen by 2, I have to also multiply the phosphorus by 2. So this is a covalent compound. Okay, so diphosphorus is the element name, and then the second one is given the "ide" ending, phosphide or pentoxide. Okay, so a hydrocarbon is simply something that has carbon and hydrogen. For naming things that are covalent that contain carbon, we always put carbon first, hydrogen second, and then everything else is in alphabetical order. So other nonmetals, bromine, chlorine, nitrogen, oxygen, phosphorus, sulfur, whatever you can think of, X, Y, Z, W, R, T, I don't know, S. So for things that contain carbon, we always put carbon first and hydrogen second, and then the rest of the elements come after that. Okay, so now we're going to use a percent composition. To do this, we're going to say in a 100-gram sample, .207 grams are carbon, and 16.793 grams are hydrogen. Make them crazy. And then all the rest of the steps are the same. We're just starting with percents instead of masses. So here I have something that looks like 2.4 over 1. I'm going to multiply it by 5 over 5. On this page, this is like the least obvious and the highest we go. Okay, so this last one is, it's for caffeine, one of my favorite drugs. We're gonna come up with the empirical formula, and then with some more information, which is the molar mass, figure out the molecular formula. So same idea, we're doing the empirical formula. And I forgot an element. So it also has nitrogen in it. So it's C, H, and then N comes before O in the alphabet. So W, X, Y, Z. We're solving for those subscripts. But we're starting with percents. The same idea. Pretend there's 100 grams and tell yourself that 49.48 grams are carbon.
So when you eventually divide this, do you divide it in like the order of like greatest to least? Or
I pick the least, and everything gets divided by the same thing. So everything will be divided by the smallest number. It's like we're making the assumption that the smallest number is there's one of these, and then for every one of these, there's 2 of those or 2.5 of those. Yeah. So because oxygen is what there's least of, we're dividing everything by 1.03 moles of oxygen. So we're assuming that we said oxygen with Z, that Z equals 1. So starting with percentages, even though there's 4 elements, the process is the same. We came up with an empirical formula, which is what we can figure out in the lab, but it may not be the actual molecular formula. So in order to solve this problem, the next piece of information we need to be given is what the molar mass is, and we are, so we can keep going. So right now I'm going to figure out what the empirical mass is. If I have 4 carbons, 5 hydrogens, 2 nitrogens, and an oxygen, what does that add up to be in units of grams per mole? So EM stands for empirical mass, the mass of the empirical formula. So I know that my EM is, 97.11 grams per mole. And I'm told that the molar mass is 194.9 0.19 grams per mole. And let's see what that ratio is. Ah, 1.9996. So the molar mass is twice what the empirical mass is, which means the formula for the actual molecule, the molecular formula, must have twice as many everythings, twice as many carbons, twice as many hydrogens, nitrogens, and oxygens, because this ratio is 2 to 1. Sorry, my page is so small. I don't know if the different colors help keep track of what's happening. Maybe not. Maybe not.